Thank you. Thank you for introduction. And yes, first of all, I'd like to thank organizers for inviting me this great workshop and this great place in Busan. And actually, this is first time for me to visit here. And yeah, I hope today's okay. Today's talk will develop the next study and yeah, and I came back here again. Yes, I will come back here again soon. But anyway, yeah. So first, I'd like to introduce myself. Now I'm a senior research scientist at RIKEN AIP, and AIP is the kind of a AI study institute in RIKEN. And I'm also visiting research at Keio University. And I have a GitHub lab repository. So if you are interested in, please access to this. And my background is actually, I got my PhD in theoretical physics. So of course, I know quantum mechanics, particle physics, and some things. And beside it, once I got my PhD, I changed my research field slightly, and it's not slightly, but maybe it's a big change. But yeah, I began to study machine learning and deep learning, in particular, so-called generative models and reinforcement learning. Actually, I have no paper on reinforcement learning, but and I focused on this study of generative models recently. And today's talk is, as you can see in my title, today's talk is a kind of the combination of my background and my recent interest. So today's take-home message is that physics can contribute to the study of the machine learning. Yeah, and I know there are many research that applies machine learning to the study of physics, but inverted direction. Yes. So this is a table of contents today, and I guess I have 45 minutes. And I just plan to introduce one section within 10 minutes or something. And yes, and in the first section, I'd like to introduce the basic concept of the machine learning and generative modeling. And in the second section, I will introduce the recent cutting edge technique of the generative model, so-called diffusion models, from a purely mathematical perspective. And in the section 3, I turn to how to interpret that kind of the concept through the physicist view. And in the final section, this is not the, section, not the, I'm just try to be ambitious, and I'd like to say some outlook on the future research on this direction. Yes. I'm sorry. Yeah. So anyway, let me start the first section. So the introduction of the machine learning and generative modeling. So this is my definition of the machine learning. And the assumption, yeah. So assumption is that, of course, as you know, the machine learning needs the data, of course, but the data can be regarded as a kind of sampling from the underlying data generating distribution. Here I denote it as a P data. So the data X is a sample from this probability distribution. No one knows. Sometimes we know the target probability distribution, but in many cases in the machine learning application, this is just an assumption, and we regard the collection of the data as samples from the one target distribution. Yes, it depends, but this is one of the my favorite definition. Yes. So the purpose is that the prediction on new data that is coming from this same data generating distribution. if we can predict something about this new data, then it means that we can predict the future from this perspective. So let me show you some example, very toy example. Please observe these 4 figures and labels. And first figure is labeled by A, and this is B, and this is A, and this is B. Then, given this data, I guess everyone can easily label this data and this data. This is, of course, A, trivially. This is B. But in order to do this kind of the process just based on the computer, then we need to program how to process this kind of the procedure. So, yes. So machine learning is one of the way to do that kind of thing. Yes. So in this context, we can show each ingredients of this in this picture. This example, in order to make data, of course, there are some writer, the data generator. And from writer, by writing something, then data is generated. And based on this data, we are trained in the previous slide. So this is completely in this machine learning definition. So in this context, the writer corresponds to the data generated in distribution, and the data corresponds to each figure and this label. And this machine learning agent corresponds to all of you here. And yes, so based on this definition, we can classify many machine learning fields. For example, if we focus on the data expression, then if the data is kind of the pair of input and output, then the corresponding machine learning algorithm is classified as a supervised machine learning. And if the data is just input data, then it is called unsupervised and something like that. And this is a classification based on the data expression. But we can classify not only this data expression, but the timing or the when the data is coming. So for example, so-called offline data or batch offline learning or batch learning is something like this. So first, data is a kind of collection of the data. Batch of the data is coming from the underlying distribution. Then that's all. Model cannot access to the distribution itself, but model need to do something. Model need to be trained within this first given data. That's called offline learning or batch learning. Oh, yes?
But how to evaluate the usefulness of data? So sometimes data may be useful, but sometimes useless.
What do you mean the useful and the usefulness? Useless?
If you just give some data, then okay, machine is running, but this data is somehow fake, then machine will get wrong viewpoint.
Right. Yes.
So first we have to evaluate the usefulness of the data, but how to evaluate the usefulness?
So purely, from this perspective, there's no way to distinguish usefulness. But there are some machine learning technique to detect this is good data or bad data. So from that point of view, I guess the information of the usefulness is encoded in the data, of course, but it's implicitly encoded into this underlying data generating distribution. So so from that point of view, there's no way. But if we split, for example, the data somehow based on some certain algorithm, then it slightly changes the shape of this underlying distribution. So it's that kind of case is also in this can be handled by using distribution. I hope it answers to your question. Yeah. So anyway, this is the very yes. Yep.
From what I understand, I get that there is two ingredients. One is to mathematically model the P data, and then the other one is make calculation of the new data.
Yep.
So, for example, in the case of usual classification program, what would be the P data?
Okay. Oh, yes. So in that case, the P data is the distribution for X and Y, for example, in this case. And the X is, say, the image, and Y is the corresponding ladder.
In the usual classification program, in the training data is given.
Yes.
We don't usually the modeling of the P data.
Ah, yes. So I mean, what I want to emphasize here is that there's no need to model P data itself. I mean, let's see. So you mean that the modeling P data corresponds to the machine learning itself?
Well, I thought that this framework
Yes.
the first model of the P data and then prediction for the details.
Yeah. So the modeling of this P data itself corresponds to the user classification task in this definition. So for example, let's consider the neural network. The training of the neural network is based on the loss function. And the loss function in the classification task is one of the famous one is just choosing the cross entropy loss. But that corresponds to the minimization of the Kullback-Leibler divergence between the model prediction and the P data. As I will explain it later. Not the classification task, but the classification usual classification task is also fit in this.
So the usual classification task we are modeling is conditional probability.
Yeah, exactly. Yes. Yes. So this is the machine learning. So let me turn to the definition of generative modeling. And this is very simple. The assumption is same, but the purpose is more concrete. We first prepare as as I show here, Q. That is the kind of another controllable probability distribution for X, and we trying to approximate this underlying distribution P data somehow, just by based on the sampling. I mean, just based on this data. That corresponds. That is the generative modeling, basically. So one example, one of the famous example is the Boltzmann machine, and it's physicist friendly, I believe. The data is something like this, and by using this image, we can define this kind of the Boltzmann weight. Here, X corresponds to the one of the snapshot of this handwritten digit. And after that training, suppose we can design good energy function here. Then what we should do is just running the sampling algorithm. For example, here I show you the result of the Markov chain simulation. And as a result, as you can see, we can generate new data in this way. Yes. And another example is, of course, can be found in the generative AI. And in this case, the data corresponds to the text generated or evaluated by human. And based on this huge data, the model corresponds to the kind of the conditional probability. And as a result, first, once you input the prompt, that corresponds to the condition of this conditional probability. Then it can generate the next word or the next sentences like this. But of course, this is a probability model. The generated sentence itself is slightly changed once you repeat this sampling procedure, as you can see here. So this is also in this definition. Okay. So let me briefly comment how to train this kind of generative model. The typical training protocol is called the maximum likelihood estimation. And first, what we do is we prepare some family of probability distribution on X. And let's call this family as a Q theta. And theta corresponds to the parameter that parameterize this family. And considering the summation of the logarithm of this the value of each value of this model probability on each data and minus the 1, then considering the minimization problem with respect to this parameter theta and just choosing the exact minimum. And I mean, and defining this Q as this Q theta. This procedure is called the maximum likelihood estimation. But this corresponds to the answer to the previous question. But once we take n data, I mean, here we consider the number of data as n data, but to infinite limit, then thanks to the large law of large numbers, this summation, I mean, this average is converging to the expectation of the minus log qx here. And actually, this corresponds to, this is equivalent to mathematically this so-called Kullback-Leibler divergence between P data and model. And this Kullback-KL divergence has a similar structure to the distance. And so minimizing this distance corresponds to the minimizing the, with respect to theta over q corresponds to minimizing this distance between P data and Q. So as a result, if we ideally, if we can do everything ideally, then that gives P data equals to Q theta. That's a trick behind the generative model. And as an answer to the question, if we consider the I mean classification task, everything is parallel, and this. So that's the answer. Yeah. Anyway, of course, so far I do not explain the model structure itself, but so we can apply any model. But if we use this kind of the neural network or deep neural network, then the resulting model is called a deep generative model. And maybe you know that in this picture, on each arrows, there are some tunable parameter. Here, W, this is a matrix, and B corresponds to the vector. But anyway, the collection of this W and B corresponds to this theta. So once you write some symbolic expression of this network, then that defines a family of probability distribution. Yes. And if we apply the maximum likelihood estimation, we need to compute a minimum of minus log of this neural network, but it's extremely difficult. So in usual deep learning, people just not computing this landscape of the minus log of this likelihood, but computing the gradient of this on each point and just applying the update by this gradient. That's the usual training procedure of the deep learning. But anyway, that's the deep generative model. And recent successful models, almost all of them are based on this deep learning. So, and actually today's focus is the diffusion model I will explain later, but it's also designed based on the deep learning. So maybe, so it's, anyway, so that's a very quick review of the machine learning recently. So I'd like to switch to the explanation of the diffusion model. And actually, but I'm sorry, this is in Japanese, but yes, yes. Yeah, I wrote some review paper. So if you are interested in, please Google this title. And Yeah. So yes. So first, I'd like to start the explanation of the data, identifying the data itself as a high-dimensional vectors. So this is well-known, one of the snapshots from the well-known dataset MNIST. But if we pick up around here, we can find, you can find that there are some numbers on each point. So just align these numbers that corresponds to defining the huge dimensional vector. So in that sense, this data point corresponds to the high dimensional vectors. So if the image itself is a color image, it's same. Just we split 3 degrees of colors, and the data is a kind of collection of these huge numbers. So it's in similar situation. So the image is a point in the high dimensional Euclidean space. So here I show you as if it is 2-dimensional, but please imagine this is quite huge dimensional Euclidean space. And the image corresponds to each point. For example, here, may corresponds to this kind of the cat image, so something like that. And the image data, if we gather if we collect the image data, then it shapes some, distribution here. That distribution corresponds to the P data. And in diffusion model, we first destroy or corrupt this data structure by making use of the stochastic differential equation here. If you do not, if you are not familiar with this kind of the concept, but please regard first term corresponds to the usual term, fourth term in the ordinary differential equation. The second term corresponds to the kind of a Gaussian noise. So based on this, so in order to define this equation, of course, we need to fix the function ft here and gt here. By the way, the time dependence is written as a subscript here. So the subscript is not the derivative, but this is a function with respect to t. And then, yes, so first you define this equation and you fix initial condition. Then it defines the moving of the each point here. So for example, if we apply, if we pick up initial point here and applying this dynamics, then this initial point slightly changed at the next step. And in the next step, it's also deviated. And in the end, it becomes like that. So in the end, this point is far from the initial point. But anyway, and in image level, this corresponds to considering this kind of the process. And in the end, it looks a little bit out of structure. But if we corrupt perfectly, then everything becomes random. Okay. Yes.
Where is the profile of the E in the spiral?
Yeah. So this spiral, this spiral is just for the presentation. It's just fake. It's imaginary one, but so
So I just want to understand where is the information of the EEG and where is the information of the probability.
Yeah. So the information of the image corresponds to the coordinate of this space. Yeah. So this image corresponds to the huge dimensional vector. So that corresponds to 1 point. I'm sorry.
Every point is the information of the colors.
Yeah. It's also is embedded as the coordinate of this space.
And then where's the information of the probability?
And the probability, yes. So For example, this image defines 1 point, so maybe it corresponds here or something like that. But the different image corresponds to a different point. Yes, yes. So the collection of this point clouds corresponds to the probability distribution. If we take the number of image infinite limits, then
So every point has related to just one image, right?
Yep.
Yes.
Yes.
And the reason you have many points is because you are connecting one image to some probability.
No. Each point corresponds to here. I show you as let's see. Oops. So just imagine each point corresponds to the natural meaningful image. But in this huge dimensional Euclidean space,
Every image is different.
Different. Yes.
Different images for
Yeah.
different cats, for example.
Different cats, for example. Yeah.
Oh, I see.
Yes. But for example, image corresponds to here, then it is expected the meaningful, meaningless image. Yeah. So the meaningful image is expected to form some shape in this huge dimensional vector.
Then what's the meaning of the spreading of the spiral shape?
So this spiral is just fake, just for the explanation.
Suppose there's a fake, but it's changing.
Yeah. So for example, it sometimes happens that this direction corresponds to the color of the cats or color of eye color of the cats or something like that, or the let's see, the length of the cat itself, or I don't know, arm or something like that. So that kind of the meaningful information corresponds to the it is believed to corresponds to the coordinates of this embedded lower dimensional manifold.
Okay.
Yeah. Yes. So yes. So yes. So each point corresponds to the image. So considering the dynamics based on this stochastic differential equation corresponds to the dynamics of each point. So in image level, image is corrupted in this way. So in the end, it becomes a meaningless image. It's this process. But yeah, as I show here as a picture, if we consider all of the dynamics of the point cloud, then that should define the dynamics for the distribution itself. And actually, it is well known that we can derive the dynamics of this distribution itself, PT. PT corresponds to the distribution at time t around here, is defined by this Fokker-Planck equation. And here, F in this stochastic differential equation is in here, and GT is here. So actually by choosing good F and GT, we can derive that the probability distribution at t equals to 1 is always normal distribution. We can choose these two functions so that it becomes like that. Anyway, so the one important point is that in the diffusion model is that we can invert this point dynamics just by adding this extra term to the previous SDE. And in order to derive this equation, there are some derivations, but let me skip the derivation itself. But if we can compute this value, first we pick up the normal distribution here and just applying this dynamics and just solve it. Then that corresponds to sampling from this target distribution. So this is the ultimate purpose of the generative modeling. So
That means this diffusion doesn't generate any.
in this direction.
I mean, this direction or what?
This direction.
Time diversion, you say, and usually some process generate entropy, then time diversion must be broken.
Yes. So the point is that I mean, yeah, random. Yes. So let's see. So first, in this direction, entropy is generically increased, I guess. It depends, but generically speaking, it is expected to increase.
Time diversion.
And but let's see. So why time reversal? Because there is in order to argue that kind of the entropy increase based on this probability process, we need to.
Open system, you have some external agency, then of course.
Yeah, that intuitively it is.
So
correct.
You have extra agency.
So this term corresponds to the external agent, because this term, in order to compute this term, we need to know the shape of the distribution at time t. And if we know that distribution, of course, we can invert this dynamics in the probability level intuitively. So that corresponds to external, yeah. Or more mathematically, I guess in order to discuss that entropy increase, I guess we need to take into account the mutual information of this process itself. So of course, yeah, one of the formulation of the entropy increase based on this kind of the process is just computing the Karbach-Leibler divergence of this total distribution. But this is decomposed to the usual entropy gain and mutual information term base. That is the mutual information term has the information from this kind of dynamics. So in general, the summation of these two terms increase, but the physically meaningful process defines the kind of I mean the let's see non-zero non-zero mutual information, I guess. So that corresponds to the naive entropy increase of this probability level, but in general, we need to take into account that kind of contribution. And that corresponds to, I think, the external, yeah. So anyway, in order to compute this term, we need to know the shape of this PT. And of course, it is, in many cases, impossible because we don't know the shape of the P data. Even this P data, we don't know the shape. So there's no hope in general. So the idea of the diffusion model is just approximating this contribution by making use of the machine learning model, or more practically it is the neural network is applied. Anyway, so the purpose of this machine learning is approximation of this term, and the top-down approach is considering the this distance between target data distribution and this model distribution in the end. But the computation of the model distribution is quite hard just based on this dynamics, because this dynamic, we know, of course, the value of ST, but in order to compute the scale divergence between these two terms at time equals to be 0, then we need to integrate this process and compute the scale divergence. It's really time consuming, and but the other way is that the purpose is just approximation of this term. So just considering the kind of discrepancy between this one and this one, and try to minimize that discrepancy is the kind of bottom-up approach. But there are very beautiful work by this authors that this target, I mean, the scale divergence at time equals to be 0 is bounded above from this bottom-up type loss function. So And of course, this right-hand side is computable. And in the end, by massaging this expression, in the end, we can get this kind of expression. And all we should know is the expectation value with respect to the target distribution itself. And it can be approximated just by making use of the Monte Carlo summation. So just replacing this expression to the average of the data, and everything, every other parts are computable. So just considering this loss function as minimizing or the decreasing this loss function with respect to theta is the training of the diffusion model. Yes. So let's suppose we can get good model, I mean good theta. Then how to, there are some degrees of freedom how to generate the new data based on the model. Of course, I introduced that I introduced the model that mimic the time reversal dynamics. But we can turn on some one parameter lambda here. In our paper, we call lambda square as h. Anyway, in this paper, it is introduced as a lambda. And lambda equals to 1 corresponds to the original backward process. And this lambda is introduced so that this model is perfect. That corresponds to that is the equivalent to the gradient of the log of pt. Then in that case, this equation defines the completely same Fokker-Planck equation, yeah, with arbitrary lambda value. But anyway, this is introduced, and if we apply this lambda, introduce this lambda, lambda controls the stochasticity of during the generative process. Of course, we can turn off this lambda completely by taking lambda equals to be 0. Then this noise term is vanished this direction. And instead, we have some 1/2 terms here. But in that case, the generating process is corresponding to solving the usual ordinary differential equation, and it is called the probability flow equation. But anyway, so lambda non-zero case corresponds to this kind of the generating process, and the lambda equals to 0 case corresponds to this kind of process. So this is, as you can see, this is quite noisy. But from the previous work, it is well known among the practitioners that this stochasticity sometimes improves the generated image quality. And this figure shows that in this vertical direction corresponds to the empirical score, and its lower is better. And the horizontal axis is roughly corresponding to the lambda itself. So as you can see, there are 6 models, but in these 6 models, 4 models improved once you turn on this lambda. So stochasticity sometimes doing good, but sometimes doing bad. It is 2 ones, but I have no idea. But there are some folklore that the model S here is in general not perfect. So it sometimes make the particle to the false point. But if we have the noise term, at that time the particle is kicked out thanks to this noise. So intuitively, this kind of the kicking effect improves the generated quality. But this is just a kind of naive explanation. Anyway, that's the review of the diffusion model. So from now on, I'm sorry, also in Japanese, but from now I'd like to explain today's topic, that how to understand this kind of the phenomena based on the Feynman space. 5 minutes? Okay. So the collaborator is Yuji Hirono over there and Kenji Fukushima at the University of Tokyo. And it is presented at in ICML 2000. Yeah. Anyway, okay. So the idea is that one way to consider it, switch the formulation from the SDE to the path integral is based on the discretization of this SDE. And one of the famous discretization is Euler-Maruyama. It's called the Euler-Maruyama discretization, just replacing this dt to epsilon and this dwt to the square root of epsilon times the sample from the normal distribution. Then this defines the distribution, conditional distribution. I'm sorry, this is conditional distribution. So maybe switch and the slash, but anyway, for this next time position. This shows that this corresponds to the Gaussian distribution with mean here, this one, and the variance this one. So the probability distribution becomes like that. And we can factorize this epsilon in the numerator. And in the end, it can be approximated by this first term. Subtraction term corresponds to the differential with respect to this time. So we can get this kind of form. And actually, this function is called the Onsager-Markup function. And it is well known in condensed matter physics, I think. And the way to the path integral is considering the path probability of this total procedure. And of course, the path probability is the usual joint probability on each time. So it is defined by the first probability distribution and the second conditional probability distribution, and the next conditional one, and the final transition. And besides this first initial distribution, each conditional distribution can be replaced by the Onsager-Markup function, as I explained. And the product of this exponential corresponds to the exponential of the summation. And if we take epsilon to zero limits, then naively it corresponds to the concept of the Riemannian sum. So it can be described by this integral. So the path probability can be represented by this kind of the path integral measure, path integral weight. But one thing I think it's interesting is that we can derive the inverted direction of this expression. I mean, in this first expression, we start from P0 and the transition. But we can massage this product between P0 and this exponential to arrive this expression. Then we can derive the form of this L tilde here. And it turns out that this L tilde corresponds to the exactly the inverted SDE Onsager-Markup function. That looks nice. And in addition to that, we can compute the loss function based on the path integral technique. It looks a little bit weird for mathematicians, but physicists can compute this correctly. And this term can be computed using a path integral technique. And that turns out to be the well-known the bottom-up type loss I showed you in the previous slide. Okay, so in this sense, the formulation of the diffusion model itself can be formulated based on this path integral idea, and I'd like to turn to the mystery of the stochasticity in the generative process. So generating SDE was this one, and of course we can write down the corresponding path probability, making use of this model Onsager-Markup function here. And as I said, we can take lambda to 0. That corresponds to the ordinary differential equation. But in that kind of the phenomena can be regarded as a kind of the probability acceleration phenomena because lambda to zero limit corresponds to considering the variance zero limit of the Gaussian distribution that defines the Dirac delta function. So everything becomes deterministic also from this perspective. That's lambda to zero limit. But up to here, we noticed that this process looks really similar to the limit from quantum mechanics to the classical mechanics. And in this quantum mechanical system, people can consider the WKB expansion. I mean, the expansion of the kind of expectation value with respect to the Planck constant. And in this case, Planck constant corresponds to lambda squared. So we expected that it is also possible to do similar expansion. And we can do that kind of computation. And actually, this kind of the machinery enables us to compute the log likelihood of this target distribution at time equals to be 0. That corresponds to it can compute the KL divergence at time equals to be 0. So, but it is, of course, the expansion with respect to lambda squared, but we can compute this first coefficient. It looks a little bit complicated, but it can be. And everything is computable, at least in lower dimensional data, just by making use of this information of the model. So we can compute the contribution of the stochasticity based on the model. And we checked that in each case, the KL divergence seems to be improved. So it is this is consistent to the well-known work I showed you in the previous slide. Yes. So based on this work, I believe that we can provide one of the answer to this folklore because this contribution, just by observing this contribution. So this result is just based on the empirical score. So compared to this situation, I believe it is the situation is quite better. Anyway, but I guess yeah. So this was our work. So I thought if I have time, I show you this final section. Is it okay to? Yeah. Okay. So yes. So far, I just comment on our work, but from now on, I'd like to say some outlook by myself to this direction of the study. So one motivation is considering the multimodal generative model. So what is a multimodal generative model? So in usual generative model, in each domain, for example, writing pictures or writing text or generating some sounds, in each domain, we prepare data and the model is different and trained individually. But the multimodal generative model is this model is unified somehow and controlled everything by one single model. And actually, nowadays, as you can see in the ChatGPT or Gemini, it can treat text or image or some other formats. So that kind of the model is a multimodal model, but basically it is achieved by combining the diffusion models and autoregressive. And the diffusion model controls basically the sampling, drawing something. And the other field is based on the autoregressive model. But if we can unify this picture just by using diffusion model, then the diffusion model is really easy to understand just by making use of the physics context. And mathematically, it's also have very rich structure. For example, the Fokker-Planck equation or Kolmogorov equation or something like that. So maybe if we can turn to this kind of the direction, then we can, I mean, our theory researchers can contribute more. And my background is, as I said, physics. So if we can realize this kind of situation, physics of multimodal model can be studied from this perspective. And in order to do that, as I said, the image can be regarded as a point in the huge dimensional Euclidean space. So conceptually, it is the degrees of freedom is continuous. So considering the probability distribution in continuous space, so schematically this situation, but the text is discrete. So the probability distribution for text has this kind of a shape. So we need to do something different because the diffusion model is basically based on the continuous variable so far. So, but actually there are some work on extension of this, diffusion model machinery to discrete variables, but no promising models in language processing up to 2023 or 24. But recently, there are some works reporting this discrete diffusion model can work on the natural languages. So it may open up the road to physics of large language model or multimodal model, I hope. So mathematically or physically speaking, the diffusion model so far, as I said, it's based on the continuous variable. And this distribution at time t follows the Fokker-Planck equation. The target is this kind of the derivative of log likelihood. But the discrete diffusion model case, the degrees of freedom x becomes completely discrete in this way. And the time evolution of the distribution corresponds to the classical master equation, or mathematically speaking, it corresponds to the Kolmogorov-Ford equation. But anyway, and the target is, of course, we cannot take the derivative of this with respect to x, but we can do something similar by taking this kind of the subtraction, differential. Yep. So, and actually, the continuous variable for physicist point of view, okay, yeah. Continuous variable corresponds to bosonic degrees of freedom, and maybe discrete variable can be realized as a fermionic variable. This is just a hope. And the text is also can be regarded as a kind of target, physics target for physicists, because, for example, this kind of the sentence can be decomposed to this kind of the tensor product, and actually we can reformulate the discrete language model just based on this kind of the tensor product approach. So it may work somehow, but actually I'm working on this kind of direction now, but it's a work in progress. Yes. But let me do this within a few minutes. Yeah. So the different direction is, I think, interesting is called maximum entropy reinforcement learning. So this is a picture for the usual reinforcement learning. This S corresponds to the kind of state of the board, for example, like Go or I don't know, chess or something like that. And this A corresponds to the next move. And R corresponds to the rewards to the player. And in usual reinforcement learning, the player or agent tries to maximize the summation of this reward. But we can turn on this contribution here. This H is computed by minus log of this value of this probability of the agent. And T corresponds to the kind, T is just one of the hyperparameters that corresponds to the temperature in physicist point of view. And one of the interesting mathematics from this paper is that one of the optimal situation can be realized by making use of this kind of the Boltzmann weight. And in this sense, the next move corresponds to sampling from this Boltzmann weight. And actually, we can implement this kind of the sampling based on this stochastic differential equation, of course. So it can be naturally combined to the diffusion model. Actually, there is a work. So maybe if we can apply our method to this situation, then it can open up the study of the physics of reinforcement line. Anyway, so thank you very much. This is the end of my talk.